When measuring geometry, human intuition relies on size, but in topology, the true measure of a space is whether its structure can be inescapably contained. The central problem topologists face is defining the exact mathematical boundary where a space stops behaving like a finite object and starts acting infinite. To locate this boundary, we have to compare two foundational test subjects, the infinite real line, denoted as R, and the closed unit interval spanning from 0 to 1. If you zoom in close enough, these two spaces are structurally identical. A tiny segment of the infinite line looks exactly like a tiny segment of the bounded interval, yet at a macro level, their global properties diverge completely. We need to determine exactly how and why this divergence occurs. Mathematicians capture this divergence using a property called compactness. Compactness is the topological language describing a space that, despite containing infinite microscopic points, can be treated as a finitely manageable, observable object. The strict definition states that a space is globally compact if every single open covering of that space contains a finite subcollection that still covers the entire space. Topologists prioritize this specific property because it provides a logical bridge. By isolating a finite subcover, mathematicians can apply the safe, predictable rules of finite logic to sets that contain infinitely many points. Let's test the closed interval from 0 to 1 against this definition. We can blanket the entire segment with a random collection of open intervals. This forms our initial open cover. Because the segment is strictly bounded by its endpoints, we can systematically discard the redundancies. We are guaranteed to find a finite number of these intervals that still lock together to protect the whole segment. Now we apply this test to the left side of our screen, the infinite real line. To prove the real line fails the test for compactness, we don't need to check every possible covering. We only need to locate one specific open cover that refuses to be reduced to a finite number of pieces. This page from James Munkres Topology provides that exact countercover in example 1. It defines a covering made up of open intervals from n to n plus 2, where n represents every integer. Visually, this creates a uniform interlocking chain. We place an interval with a length of 2 centered along every single integer marker, stretching forever in both directions. If we attempt to select a finite subcollection from this chain, we run into an immediate structural boundary. A finite number of these uniformly sized intervals can only span a finite distance. The moment we stop picking intervals, the infinite tails of the real line are exposed. No finite collection of these pieces can ever cover the entire space. Because this specific covering cannot be reduced to a finite subcover, the real line definitively lacks global compactness. It cannot be finitely contained. Covering spaces with intervals is only one method of measurement. Topologists also developed an alternative, point-based tracking system called limit point compactness. Under this definition, a space is compact if every infinite subset of points placed within it is forced to cluster around at least one specific limit point. If you drop an infinite number of points into the bounded 0 to 1 interval, they have nowhere to run. Because the space is restricted, the points inevitably bunch up and pile on top of each other, creating a cluster point. We can test the real line against this exact requirement using the set of integers as our infinite subset of points. Because the infinite space allows these points to march outward forever with perfectly equal spacing, they never accumulate. There is no cluster. These two distinct tests, covering a space with intervals versus tracking clustering points, might appear unrelated. However, for well-behaved measurable spaces, known as metrizable spaces, these definitions describe the exact same underlying geometry. Looking at Munkres Theorem 28.2, we see the formal proof establishing that global, limit point, and sequential compactness are entirely equivalent for metrizable spaces. Mathematicians rely on this equivalence constantly. It allows them to swap a difficult covering argument for a simpler sequential argument, depending on the parameters of their problem. The fact that the real line fails both the covering test and the clustering test firmly establishes its inherent global instability. Despite this global failure, the real line is still the foundation of calculus. This works because a space can be entirely unstable globally while remaining perfectly predictable up close. This localized stability is known as local compactness. This definition establishes the rule: a space is locally compact at a specific point if you can draw a small neighborhood around that point that is completely contained within a compact subspace. We test this by plotting an arbitrary point x anywhere on the infinite real line. First, we define a small open neighborhood immediately surrounding our point. Next, we wrap a strictly bounded closed interval around that open neighborhood. We've successfully trapped our local area inside a perfectly compact bubble. Example 1 in the text confirms that because we can perform this exact trapping maneuver for every single point along the axis, the entire real line is locally compact. The real line stretches endlessly in both directions, making it impossible to contain as a whole. But at the microscopic level, around any given point, it operates exactly like the finite, well-behaved unit interval. We can organize these geometric rules into a clear, nested hierarchy. The broadest category contains all possible topological spaces. Within that universe, we define a stricter subset for locally compact spaces. This is where the infinite real line resides, guaranteed to be stable at the neighborhood level. Finally, we reach the most exclusive inner ring, globally compact spaces. Here we find our securely bounded 0 to 1 interval. The text explicitly notes that global compactness is the most demanding condition. If a space is globally compact, it automatically inherits local compactness. This hierarchy serves as a diagnostic map. It allows mathematicians to precisely locate where a specific space loses its structural integrity. Measuring geometry in topology requires letting go of raw distance. The true metric is the inescapability of a space's structure. Local compactness provides the rigid neighborhood stability required to make calculus function on the real line. Global compactness provides the absolute boundaries required to treat an entire space as a single finite object. The real line is like a lantern in a massive cavern. It perfectly illuminates the immediate area around you, but cannot reach the distant walls. By testing for both local and global boundaries, compactness serves as the topologist's ruler, the precise mathematical tool used to determine exactly how much of infinity can be securely managed.